In this Algebra 1 video, we're going to talk about Chapter 1, Lesson 7, Functions. Now, our objective is, it's a two-part objective. As the student, I can determine whether a relation is a function, and I can find function values. Now, let's just focus on the top part of this slide for now. If you want to skip some space for the other stuff, that's fine. We're going to talk about a function. A function that should ring a bell. We learned last year, a function is a relationship or a relation between inputs and outputs, where this is the most important part. Every input has only one output. That is the most important part. That means every time we plug in a number, it should only give us one output, one result. So that's what we talked about last year. So that's what we're going to first check now. Now you can ignore what's in the bottom of the screen for now. We're going to come back to it, maybe skip some space. But essentially, what I want you to realize is all equations, all graphs, anytime we're trying to write an equation or graph something, it is called a relation. And we talked about relations in the last video. If everything is a relation because we're somehow relating them to each other with mathematical operations, but here's the thing, there is a specific type of relation, sometimes it is a function, and that happens when every input has only one output. So now there's two ways to check. There's a visual way to check with the graph, but there's also a way to check with a table, a mapping, or things like that. So let's take a look at the visual way. Now, how to tell if it's a function. Okay, this is the visual way. We call this the vertical line test. Now, the vertical line test can only intersect, that vertical line can only intersect the graph once if it is a function. So let me show you what I mean. For example, take a look at the first graph on the top left. If we were to draw a vertical line anywhere we wanted on this graph, for example there, or let's say even there, it does not matter where we drew it, it is only going to cross the graph. In this case, that graph's called parabola, but you don't need to know that right now. Anyways, it only crosses this graph once, no matter where you draw that vertical line. It only crosses once. So because of that, this one is a function. So we're going to say, yes, it is a function. Now you're welcome to write that underneath it, above it. I'm just writing on top of it so you know that graph is a function. Now, let's look at the one right next to it. If we were to imagine a vertical line going down here, you'll notice that vertical line crossed here and it crossed here. In our last example, it only crossed in one spot. But in this one, it crosses in two spots. So because of that, this one is not a function. It would just be a relation. And we know that because the vertical line crosses the graph more than once. Think of it this way. If we were to plug in, let's say that's where x equals 2 was located. If we plugged in 2 into our equation, into our function, we would end up getting two numbers for y. We would get two values. And so because of that, it would tell us, oh, that means this one input had more than one output, and that defies the definition of what a function is. So for that reason, this one would not be a function. So just keep that in mind. Now, let's take a look at the one down below it. The one down below it, if you drew a vertical line there, or you drew a vertical line here, or here, it doesn't matter where you draw it in all those locations, it only crossed the graph one time. That means no matter where you drew it, even though this graph is all squiggly and crazy looking, because it only crosses it once, that each vertical line only crosses it once, this is a function. So I'm going to put yes, is a function. That one is going to be a function. Now, for the one in the bottom right, let's imagine we did the same thing. If we drew a vertical line right here, essentially look for a place to draw that vertical line. I know my vertical line is a little crooked, but if we were to draw it there, in that location, we would notice it would be crossing here, here, and here. So that vertical line touches it a lot more than once. So this one is not even close to being a function. So we would say not a function. Because, yeah, we just learned that a squiggly line over here was great, but we found it only touched the graph once. But now over here, the line does touch more than once. Therefore, that is not a function. So in each of these examples we just did, where we were checking if it was a function or not, all of them were continuous graphs. So let's go back to that last slide for a moment. A continuous graph or continuous data. That's what we're going to talk about. Continuous graph or continuous data. It is a function graphed with an unbroken line or smooth curve. But you'll notice, continuous we usually use to describe functions. So technically, this one down here was continuous, but we found it wasn't a function. But that's okay. We're trying to make a point. Data in general can be continuous, and that means if you were to graph it, it would be an unbroken line or a smooth curve. So here, I didn't do any examples with lines. An unbroken line would look something like this. If that was our graph and then we graphed our line and went like that, that would be an example of an unbroken line. And yes, that would pass the vertical line test no matter where you checked. So we would say, yes, that is a function because of that. So an unbroken line or a smooth curve, meaning no gaps, no jumping around. Whereas, take a look at this one, the one right here in the middle. This one does jump, okay? But let's see, it might still be a function. And we could check by doing a vertical line test right here on the y-axis. And you'll notice, because that's an open circle, because it says it has an open circle right here, that means at that location it doesn't include y equals 2. It includes y equals -1 down here. So it only actually crosses the graph once at that location. So because of that, we would say that that is a function. Yes, that is a function through a technicality. But we will also notice this is not a continuous graph. This graph jumps. It has a gap. It has a break in it. So because of that, that's going to be our last definition, where we're going to talk about last definition for this part. Talk about a discrete function. I'm sorry, not necessarily a discrete function. They're not always functions, but they can be. But discrete data or discrete situation is a graph that consists of points that are not connected. And in other words, I like to say they have gaps. So, i.e., for example, gaps. That's tends what happens to them. So, if you ever have a graph where it goes in a straight line, that would be considered continuous, meaning all along this line, it continuously has data and never stops. So the same thing as if it had been a parabola. You don't even know that name. I keep saying that, but that's what this U-shaped graph is called. So because of that, it's continuous. There's no broken lines in it. That would also be continuous data. However, if you start seeing dots being graphed like this, that is going to be discrete. And they can even go in a straight line. Those dots are welcome to go in a straight line as if they had just gone like this. But even though they're in a straight line, if it does not specifically say it was the graph of a line, meaning if it does not tell you now draw a line through it, if it does not, that means it's just those locations. That means it's going to be discrete. And now in that example you just saw on the other screen, if you had what's called a step function, where it goes here and then it breaks, it goes here, those are called step functions. That would be discrete data. That's what that's an example of. So this is the visual way of checking if it is a function, yes or no. So how to tell if it's a function using other methods, such as a table or a mapping. And if you don't remember what a mapping is, feel free to take a look at our last video when we talked about relations, how we can describe them using things called mappings. Alright, so let's look at the table method first. This is an input-output table. If you had taken, let's say, this equation y equals half times x squared minus 1, and you plugged in each of these values to see what you would get, is you would find out if you plugged in -2, it would equal positive 1. If you plugged in 0, it would equal -1. If you plugged in 2, it would equal positive 1. So you could look at, one way to tell is by looking at its table. And if you look at this table, our inputs, -2, only had one output. It only had one number as a result of plugging in -2. Same thing with we plug in 0, we only get -1. We didn't get -1 and positive 1. We didn't get -1 and 2. We only got one output when we plugged in 0. Same thing when we plugged in 2. We only got one output. So that's one way of knowing for sure that another way of knowing that it's a function. But notice we only checked at these values. So this way might not always be as absolute, but it's usually a good indicator. Now let's talk about a mapping. So now in a mapping, so if I took those same input values and I put the input values in on the left side, and then we took those output values, we got those y values, they go on the right side. So the inputs go on the left, the outputs go on the right, or the domains and the ranges, that's another thing we can call them. So now if you do this, and you now connect what goes with what? -2 goes with 1, 0 goes with -1, and then 2 goes with 1. So in each of these, even though it looks like these two inputs gave us the same output, it's true, but that doesn't matter. The rule was every one input can only have one output. It didn't say anything about one output sharing two inputs. That doesn't matter. That doesn't hurt it. So to visually show you what this would look like, I'm going to quickly sketch the graph to show you what I mean. So if you were to do a quick sketch of a graph and then graph those points from the input-output table or from the mapping, or if you're looking at ordered pairs, you would have dots that would look something like this. So now if you made an effort to draw a general estimation of a curve that goes through those points, that curve is the graph of this function. And when we look at this, it looks a lot like the example we looked at right here, where we said it was a function because no matter where you put that vertical line, it was going to pass. It is still going to pass the vertical line test. It would only cross once. So this is all the different types of ways to kind of describe a function, other than its actual equation. And this is what we're going to do in order to tell if it's a function, because like I said, that was our first objective. So we fulfilled our first objective of deciding whether it is a function or not. Now we're going to do our second part of our objective. We're going to find function values. And doing this, we're going to use something we did towards the end of last year, something called function notation. But if you don't remember or you weren't here, that's okay. We'll talk about what function notation is. So before we talk about how to find the value of functions, let's first talk about function notation. Function notation essentially is equations that are functions can be written in this form. This function notation is a form. And in other words, what you're really going to do is you're going to replace the y with f of x. And so that's f of x. That's pronounced f of x. So we're saying function f that relies on x, meaning x was the input. We wouldn't know the value of the function until we had an input for x. An example of that is the one on this last screen. This function relies on x. Once we plug in for x, like we did here, we would then have a value for y. Y is the output. Y is the dependent variable. So, for example, because this one was a function, we could change that y to an f of x, to an f parenthesis x. That's just the generic one we tend to use, f for function. So function f that relies on x, we can now rewrite that, and you're literally just replacing the y with it. So everything we've ever learned about equations, lines, especially lines, is exactly the same, but instead of y, you'll just see this symbol f of x. That's essentially what we're saying for it to be function notation. As a side note, you can also, if you have more than one function, you can have a function g of x where g depends on x, and that's even assuming that x is the letter of your input. If the letter of your input was something else, you could technically have something like g of a, meaning function g that relies on a to be plugged in to know what it's going to be. So an example of a g of a could be like, we could say g of a, function g of a, is a squared plus 1, meaning a is our input, and so that's why this function depends on a. That's kind of what we're saying there. Now, before we go on much further, I want to point out there are different types of functions. So there are linear functions, such as, let's see if this example on the bottom left. It's a line, and we've graphed lines before many times in 7th grade. There are linear functions, but then there are also non-linear functions, such as this. I keep calling it parabola. I'm naming it. It's called a parabola. That is an example of it was a function. We said yes, but it was not linear, meaning it was not a straight line. So make sure you can easily visually determine whether it is a linear function or a non-linear function. So linear functions, linear equations, all that stuff we talked about, graphing lines, interpreting lines we did last year, we're going to do that. We can do that some more in Algebra 1 and take it to another level. So let's say, for example, we had f of x, function f, equals 2x minus 9. And you were told to maybe evaluate it, or our second objective, find the value of it. So let's say you were told find it when x equals 2, x equals 4, and x equals, I'm going to say 5. Now, if that's an ugly 5. So what that's going to look like is this. When you go to actually do it, when you actually plug it in, this is where you're going to continue use function notation. You've got to plug it in using the proper format, and I'm going to show you what I mean. Now, you'll notice that in order for us to evaluate each of these, they all start the same way. It's the same format. But here's the important part that I have not told you yet. What goes into this parenthesis right here, what you write in there is telling you, or if you were to see it, it is to let you know what was plugged in, what was the input that was inserted and evaluated with. So for each of these, because the first one, we're going to plug in x equals 2, we're going to put a 2 right here. That means, hey, we're going to plug in 2 for what used to be there. X used to be there. So we're going to plug in 2 into x's spot. So this open parenthesis is where x used to go, so that's where the 2 is going to go. and so on for the rest of them. We're going to plug in a 4 for that one, so say f of 4, the function of 4. Well, it's the function of x when we're evaluating 4 is essentially what we're saying. So put in a 4 over here. Now for the 5. Now, when you now go to evaluate these, I want to point out, you never do anything with this left side, ever. You don't do anything with it, because this is not saying f times 2, f times 4, f times 5. It doesn't mean any of those things. It only means that it's just a label. Hey, we plugged in 2. Hey, when we put in 2, we got out, and let's find out. Let's evaluate each of these, using the order of operations, of course. So using the order of operations, we can know what each of those what the output would be. So we could write our final answers as saying f of 2, meaning in function f, when we plug in 2, we got -5. When we plug in 4, we get out -1. When we plug in 5, we get 1. So we can almost write our answers in function notation as well. And yes, all of these can be translated to ordered pairs as well, like so. So let's take a look at these examples. Let's say we're finding function values. Let's do a few examples. Now for some of these, for the first couple, kind of follow along, but then for the last few, I want you to actually hit pause and try them on your own. So if we were given function f and function g, this would be given information. Now what we're going to be given questions asking us to do something with that information. For example, it'll say f of q plus 1. Meaning they want us to take function f, and remember what goes in here is what we're plugging in. That's what we're going to do. So first things first, write out the function where you just show an open parenthesis where x normally goes for function f specifically. That's what we're doing. Now we're going to actually take the time to plug in for each of those items. We're going to plug in q plus 1 in the place of where x used to be. Now, I know it seems we're not plugging in a full number, but we don't need to, because now we're going to use what we learned about the distributive property. 6 times q, 6 times 1, and so 6 times q is 6q. Now, I'll actually show my work for that. Let me hit pause. So I'll actually show the work. 6 times q, so we have 6q plus 6, and that plus 7 is still there. Now our final step is just to combine like terms with everything we have. So if we do that, we'll be left with 6q, and now plus 6 plus 7, that's positive 6 plus 7, that means plus 13 or positive 13. So that tells us f of q plus 1 equals 6q plus 13. That is the output when we had the input of q plus 1. Make sure you copy this down. Let's do a couple more. Now take a look at this example. F of 2 plus g of 2, meaning take function f, plug in a 2 for x, then go to function g, in this case plug in 2 again. It doesn't have to be the same number, but in this case it was. Plug in a 2 for x, evaluate both of those, and then you're going to add them together. That's what we're going to do. So if you think you already can do that, press pause and try it, and then see how you did. So it should look something like this, where I took function f is right here, and I plugged in 2 for x. Then I took function g and plugged in 2 for x as well. Now just use the order of operations, simplify, and combine everything you can. On the left side, we have 12 plus 7, which equals 19. And then on the right side, the g, we have 4 minus 4, which becomes 0. So 19 plus 0, well, that's just 19. So that tells us f of 2 plus g of 2 equals 19. That would be our final answer. So on this screen, I've now given you quite a few more examples. I want you to hit pause and I want you to try. Write them on another scratch sheet of paper if you're not sure yet, or simply write them lightly. I want you to try each of these. And remember, what's inside the parentheses is what you're plugging in. For function f, you're going to plug in -3 for x. For function f, you're plugging in m. For function g, you're plugging in -4t in x's place. That's what I want you to do for each of these, and then check and see what you did. Hit pause, try these, and then I'm going to show you the answers. I'm not going to take time to explain all of them, but I wanted you to have some practice with feedback. If nothing else, at least copy these down. After you try them, of course. So now take a moment real fast and check your answers on each of these, and then see how you did and reflect back on and see if there's anything you could improve. If you got the correct answer, sweet. If you didn't, maybe check to see what did you maybe plug in wrong. And I'll give you a hint: when you plug things in, use parentheses so you make sure you don't fall out of the order of operations. Here's what I'll do. If you're not sure how to get some of these answers, I'm going to press pause and I'm going to work out each of these. I'm not going to explain them, but then I'll take a couple seconds and I'll flip through each slide. So if you need help with that example, just press pause and give it a shot. That's what I'm going to do for each of these. then I want to make sure you have the correct answers to the correct steps. Then we'll be all done. Alright, so now go through each of these and hit pause if you need time to write it down. Here's number 3. Plug in negative 3, order of operations, combine like terms, you're done. Plug in m, literally you just replace the x with the m since there were no operations to do. You can't do 6 times m, it's just 6m. Plug in r minus 2 in x's place. Well look, you now have an option to do the distributive property. Do the distributive property and then combine like terms and you're done. For this one, just plug in 5, follow the order of operations, combine like terms, and you're done. Plugging in a and then adding 9. The question was g of a, meaning you're plugging the a, but then it wants you to add 9 to all of that. So plug in a into x's spot, becomes a squared. Then you still have to add that 9. So negative 4 plus 9 is positive 5. Plug in negative 4t into x's place in the function g. Negative 4t times negative 4t, negative times a negative is a positive, t times t is t squared. And then you're done. Just make sure you have it in proper function notation. Last but not least, plugging in negative b in its place. That means you have negative b squared. That means negative b times negative b. Negative times a negative is a positive. B times b is b to the second power. And then minus 4 just comes along. Alright guys, so we've now fulfilled both our objectives. We have talked about how to determine if it was a function, and we have also talked about how to find the value of a function. And I hope you copy down these last few examples because these are going to be good examples for you to now study from and base your future practice problems off of. Good luck. Let's come to class prepared. Take care.